So in this section, we're going to go through division. And really, I want to show you another method that isn't actually in your book, but this way you can kind of see another process if you prefer that. So anytime we're given a polynomial of degree n, we can always divide it by a polynomial of the same degree or one that's smaller. So you can divide a third degree by a second degree, first degree, or 0th degree. You can take a 10th degree and divide it by a 10th degree, 9th degree, all the way down to first or 0th degree polynomial. So this first method I'm going to go through, long division, works more generally, which is why I want to show you it. So we're going to take the polynomial negative 9x to the 6 plus 7x to the 4th minus 2x to the 3rd plus 5 and divide it by this piece here. So what you can think of it, it's the same thing as your normal division. 7 divided by 3 is 7 over 3. Same type of process works here. And so we're going to go through this just like we would long division in elementary school, how you guys learned it probably when you were growing up. So you want to put what you're dividing underneath your bracket, and then you're going to put the thing you're dividing by on the outside. And the whole goal is you want to match those coefficients. So I want to take this highest term we have, and I want to match the term right here. So this is going to be our process every single time. Match these two up. Well, to get 3x to the 4th to be exactly negative 9x to the 6th, I've got to go ahead and multiply that by negative 3x squared. So negative 3x squared times 3x to the 4th will give me this 9x to the 6th. So now what I'm going to go do is I'm going to take this term that makes us match, and I'm going to multiply the entire thing we're dividing by negative 3x squared. So when we do that, negative 3x squared times 3x to the 4th gives you 9x to the 6th. Negative 3x squared times 2x is going to give you positive 6x to the 3rd. And then negative 3x squared times 1 gives you negative 3x squared. So the one thing you want to be careful about is if you look at the original thing we're dividing by, I don't have every single term in here. But when I did write this, I included all those missing pieces. And it's mostly just to be able to make that so that things line up nicely. Like when I multiplied by the 3x squared, I've got an x squared term here, but I didn't in my original thing. So it just allows us to line things up pretty cleanly. So what I'm going to do now that I've multiplied by negative 3x squared is I'm going to subtract this from the original polynomial we started with. So if you take negative 9x to the 6th, subtract negative 9x to the 6th, those will cancel out. And then I'm going to bring any terms that I haven't used down. So you would bring this 0x to the 5th, but there is none. We'll bring these down. When you combine negative 2x cubed and negative 6x to the 3rd, you get negative 8x to the 3rd, and then keep going through this process over and over. Now we're going to do the same thing again. I'm going to make this first coefficient match the power here. And the way I need to do that is I just need to multiply by 7 over 3. So I'm going to keep note up top that I have to multiply this first leading term by 7 over 3 to make them match the same. So I'll distribute that to everything, the 3x to the 4th minus 2x plus 1, to go ahead and get 7x to the 4th minus 14 over 3x plus 7 over 3. And I want to go ahead and subtract this from what was remaining. So if we do that, the 7x to the 4th cancel, bring anything down, and you end up with this piece. So you keep going through this process. Now I have x to the 3rd and I have x to the 4th here. Because my remainder has a smaller degree than what I'm dividing by, I can go ahead and stop this process. So you keep going until what you end up with is smaller degree. So each of these pieces does have a specific name. The thing that goes underneath the division sign is going to be the dividend. The thing you're dividing by is the divisor. The piece that goes up top is called our quotient, and then everything left over is going to be our remainder. So what we can do now is we can write our result in a couple different ways. We have the dividend over the divisor. It's going to equal the quotient. So the piece we had up here, plus the remainder divided by the divisor. Or if you just rearrange this, the dividend is the quotient times the divisor plus the remainder. So from this prior example, you could rewrite it in two different ways. You're going to get the quotient plus the remainder over the divisor, or you get the negative 9x to the 6th plus 7x to the 4th minus 2x cubed plus 5 is the quotient times the divisor plus the remainder. So this works more generally when you have higher degree polynomials you're dividing by, but synthetic division is a much cleaner way. The only negative to it is it only works in a very specific example. So this will be the main type of division we're going to focus on, but if you like doing the long division, feel free to use that. So the thing is, this only works when the polynomial is divided by a single binomial that has the form x minus a. If you're dividing by a second degree, third degree, anything else, this method is not going to work. So it's very selective in what you can do. So best thing we can do is go through an example to actually see how this thing is set up. So let's take a look at this division. So we need to figure out what the value of a is because it's the form x minus a. So you have x plus 2 you're dividing by. That's x minus negative 2. So really the value of a is negative 2. So that's going to go up here in this little box. We're going to put our value of a. What's going to go on that first row are all of these coefficients that are out front. And you want to include any zeros again. So it's really important. I have a fifth degree polynomial. Do I have every single piece? And in this case, I'm missing those x cubed terms. So what I like to do up top is I tend to label all of the powers. It's a fifth degree polynomial. I'll go down the list and we end at x to the 0 power. Now I'll put the coefficient of each of these in the row underneath. So we have 1x to the 5th, negative 4x to the 4th. We have no x cubed, 3x squareds, negative 2x, and then our constant term is going to be 1. So the process that we're going to follow is we bring that first coefficient down, so we get 1. To figure out what number is going to go next, we're going to take the negative 2 times it by the 1, and we get negative 2. We'll add those together, so negative 4 plus negative 2 is negative 6. And now I'm going to repeat the same process. I'm going to take negative 2 times it by negative 6. That gives me positive 12, so that gets moved here. Add them together, multiply this number by negative 2, add them together, multiply that number by negative 2, add together, multiply by negative 2, add together. And now I can go ahead and stop, and this last piece is going to be my remainder. So you're going to keep multiplying the number you get underneath by a, add it to the next coefficient. So you can kind of think of it like you're taking x to the 5th and dividing it by x. So these numbers give you the coefficients of each of those smaller terms. So it was x to the 5th. The first number becomes the coefficient of x to the 4th. Then x cubed, x squared, x to the 1st, and so on. So now we can go ahead and pick off our pieces. Our quotient we'll call q of x. We have 1x to the 4th, negative 6x cubed, 12x squared, negative 21x, and then our constant term is 40. So this is going to be our quotient. And the nice thing is our remainder, which will be r of x, is always going to be just a constant number. And this will work anytime you're able to use synthetic division. So here our remainder term is negative 79. So now we can rewrite this. Our original division we could write as our quotient plus our remainder over the divisor. Or you could multiply by the divisor and you get another way to express that. So let's go ahead and try this again. Let's take this polynomial and divide it by x plus 1. So in the box over here, I'm going to put the opposite. It says positive 1, we put negative 1. Now I'm going to put the leading coefficients. I've got an x to the 4th degree, go all the way down to x to the 0. So I have negative 11 x to the 4th. I've got negative 2x cubed terms, negative 8x squared. I have no x's, and then negative 4 is my constant term. So I bring the negative 11 down. I multiply the negative 11 by negative 1. That gives me positive 11. So now I add these two together, multiply by negative 1, add together, multiply by negative 1, add together, multiply by negative 1, add together. So I started with x to the 4th, so now I'm going to start with my x cubed terms. So this division is going to equal negative 11x cubed plus 9x squared minus 17x plus 17 plus our remainder over our divisor. Okay. So let's do one more. We've got x minus 1, so we're going to put a positive 1 here. We have one x term, 8 x's, and negative 9 is our constant. So we bring the 1 down, multiply it by 1, gives us 9, multiply by 1 gives us 9, and we add it together this time and we get 0. So really when I go through this division, I'm going to get x plus 9 plus 0 over x minus 1. And if you really notice, this thing factors pretty nicely. So I'm dividing out by a factor, and we've got a remainder term of 0. So in that case, if you go through and divide by this linear term, the remainder is 0, the divisor will be a factor of that dividend. So this tells us about a special theorem that's called the remainder theorem. So if you have a polynomial f of x and it's divided by this binomial x minus k, the remainder is going to be what the function is evaluated at k. So if the remainder is 0, that tells you it's a 0 or a factor of the polynomial. So let's go ahead and try this out, and we'll do it two different ways. We've got a polynomial. We want to find what the polynomial is evaluated at negative 2. And we're going to do it directly and by the remainder theorem. So doing it directly, you just plug in negative 2. So that gives us 2 times negative 2 cubed minus negative 2 squared plus x, so minus 2 minus 4. So that's going to simplify pretty nicely after we go through all this addition and subtraction to negative 26. So now let's try it with the remainder theorem. What we want to do is we want to take our polynomial and you want to evaluate it at negative 2. So we're going to divide it by x minus negative 2. So pretty much if you want to evaluate it, that number is going to be the one that gets put off in the box upside. So I've got 2x cubed terms, minus 1x squared, 1x, negative 4 is my constant. So I bring down the 2, multiply by negative 2, add together, multiply by negative 2, add together, multiply by negative 2, and add together. So the thing left over is our remainder term, or our remainder, so that tells us p of negative 2 is negative 26. So either method is going to work. The benefit of doing this is if it's a 0, it's going to help you with factoring, which is something we're going to spend a lot of time with in the next section. Okay. So let's go ahead. We're going to use synthetic division to find p of 1 if this is our polynomial. So we're going to put 1 off to the side, and I'm going to put all of our coefficients. So we've got 1, negative 4, 9, negative 6. Bring the 1 down, we get 1. Multiply by 1, add together, multiply by 1, add together, multiply by 1, add together. So in this case, that tells us p of 1 is going to equal 0. So remember, when the output is 0, that's going to be where you cross the x-axis. So it's called a 0 of the polynomial. So the zeros are going to be the x values of the x-intercepts of the graph. So this is going to be important because this is going to help us with graphing, and it's going to help us with being able to factor and get a full picture of these polynomials in the future.